So, morning everyone. This is lecture number 5, ME210 Fluid Mechanics. And today we'll be starting a new topic which is called Fluid Dynamics. Okay. We have a few sections remaining from the previous lecture. So, we'll finish that first and then we'll move on to Fluid Dynamics. So, let us do a quick recap of what we have been doing in the last lecture. So, let's go there. So, in the previous lecture, we completed a couple of ideas that we were talking about. Oh, sorry, this is lecture number 3. I'm sorry. Well, I don't have that, but here it is. Sorry. So we talked about the pressure for the force because of the spatial gradient pressure, and this was equal to rho times grad p with a negative sign. And then we did a force equilibrium on static flows. So we took a situation where we have the Earth's gravitational field, and based on that, we found out that grad p is equal to rho times g. So we figured out that the constant pressure lines are always perpendicular to the direction of force field. Okay. So then we found out through integration what is the pressure distribution in liquids and gases in the Earth's gravitational field, of course. Then we talked about non-inertial systems where you may have an acceleration in the system. So if you stay in the system coordinate system reference, then you have to add a pseudo force because your system is non-inertial. And we took two situations. One was a linear acceleration and one was rotation, rigid body rotation of the fluid. Okay, so we found out the pressure distribution in both cases. And for the rigid body rotation, we found out that the pressure distribution was parabolic. So we have these paraboloids of rotation that are formed as constant pressure surfaces. And then I asked you to find the path a particle may take if you leave it in that kind of a pressure field. Well, so a buoyant particle. And what you had to do was to find the force field lines in this case. Okay, so you had to find those curves whose slope is always perpendicular to the paraboloids that we talked about. Okay, then we moved on to immersed surfaces. So if you have a surface that is immersed in a liquid at an angle or in a fluid at an angle, so then you have to find the net force as an integral in this case. And when you do that, you will figure out that was left to you that the net force acting will be equal to pressure on the center of gravity of the surface times the total area. So that makes our lives much easier if you have to calculate things. And if you have to find the net moment, well, in fact, if you have to find the net moment, then you'll see that the moment is concentrated at a point which is below your center of gravity, which is obvious because the force distribution in this case is such that the force is larger towards the bottom half due to the increased pressure downwards. Okay, then I shared, I did not do the derivations with you, so that was shared with you over Moodle. Right, so that is what we had done in the last lecture. So we have two topics left, two minor topics that we'll finish off today and then move on to fluid dynamics. So the first one is called hydrostatic forces on curved surfaces. So if we have a surface, a solid surface, which is curved, something like this, and this is immersed in a liquid. So you have liquid all around it. Right. So because of the pressure in the fluid, you will have some sort of force acting on this curved surface. Now, let us assume that this curved surface is, let's say, it could be the case that the curved surface, on the other end is there's no liquid. Okay. So if it was a very thin surface, then the liquid, the forces on both sides will balance each other. But let us say in this case, we have this kind of a situation, and we would want to find out what are the forces acting on this curved surface so that we can apply an equal and opposite force to this whole block that is there to balance it. So let us say that was the kind of situation, or it could be a ship and inside there is atmospheric pressure. So you have to apply some force to balance this liquid pressure from the outside so that the surface does not bend or break or something. Right. So we can break the total force into a horizontal force and a vertical force, the balancing forces. And in fact, to calculate these forces, we don't really need a physical surface. We can just take a hypothetical surface in the liquid and try to find the forces. Now, if you had to do integration, because you know that the force acting at any point is perpendicular to that, and the value is pressure times the differential area that you have. So you have to integrate over the complete surface, curved surface, to find the total force and then take components of that. So rather, what you can do much easily, because it's a static situation, right? So static situation means that any amount of liquid that you take in this whole bulk liquid, that amount of liquid should, the force acting on that amount of liquid should be zero. That's about hydrostatics. So what we can do is we can take a hypothetical volume which looks something like this, and then we can say that, well, I'll draw a line. So this hypothetical volume that I've taken, well, let's take the bottom half first, which is this one. So the net force acting on this hypothetical volume also has to be zero because it's stationary. And what we will see is that if the force acting from the left hand side on this volume is something, then the force acting, the FH that we have to find, has to be equal to this horizontal force from the left hand side. Remember, this is our free body, so that free body is stationary, so that means the net horizontal force acting on this body also has to be zero. And on the left hand side, we know what the force is. That is, this force can be found easily because you can easily find the pressure distribution, and you can multiply the pressure on the center of gravity times the area, and that gives you the force acting on the left hand side. So FH has to be equal to that force. Okay, so this, I'll just say this is also FH, and then that this left hand side force you can easily find. All right, now FV, again, what we can do is, now we know that on the top we have an atmospheric pressure, so we can take now this whole, choose a different color, so we can take this whole liquid now, sorry, this one. Now we know on the top the force acting is atmospheric, and the force, the FV has to balance the weight of the water that is above it. Okay, so if I call this one as weight 1, this one as weight 2, and on the top you have atmosphere, so it has to be equal to the weight of the atmosphere, okay, plus weight 1 plus weight 2. Okay, and that again can easily be solved. To find weight 2, you'll have to find the volume of the liquid in this bottom part, and for that you may require some integration, but that may not be that complicated. Okay. So again, there's nothing new that we've learned here. It is simply an application of fluid statics. Okay, the next topic is buoyancy. And again, this is something that we already know. So we know from our previous experience or previous learnings that the force of buoyancy acting on a liquid. So let's say you have, on a solid. So let's say we have a solid which is fully immersed in a liquid. And this will happen if the solid density is larger than the density of the liquid. Now, the force of buoyancy acting on the solid is nothing but the weight of the water it displaces of the liquid. Okay, so if the solid was floating, then you'll have to find out the amount of liquid it has displaced by finding out the amount of solid that is inside the liquid, and then you can find the force of buoyancy. Now, this force of buoyancy is not a new force as such. Okay. So this buoyancy force is simply a net effect that we see because of the pressure differential between the top and bottom surfaces of the solid. Okay, so let's take an example here. So the same situation that we have, but if I was to draw the free body diagram, then what I'll see is that on the top surface, the force that will act is pressure times area. So let's say it's a cubical body. So the area is easy to find. And on the bottom surface, the force acting is P plus the pressure difference because of the height now, because the pressure at the bottom is higher than the top. So this we'll call rho g h, where h is the height of the block, and this times area. Okay, so the net difference in the vertical forces that you see is nothing but F net vertical is upwards because the force acting from the bottom is higher, and that is equal to rho gh times A. Okay. So rho times A can be taken together, and then you have G times H. Sorry, so we should say, so remember this rho is the rho of the liquid. Okay. The pressure difference is because of the height of the liquid. So rho L times G and H times A can be taken together, and if you do that, that becomes nothing but the volume. The solid is fully immersed, so this is the total volume of the solid, right? And that is what your FB is for this situation. Now, if the solid was floating, then you would have taken the delta H only due to the amount of solid which is floating inside the liquid. So in that case, the volume that you will get is the volume of water displaced. So actually, we should not write volume of solid here because it's not a general sense. So volume of liquid displaced. Okay, so what we see is that buoyancy is not a new force per se. It is simply a net effect that we see because of the pressure differential force. The difference in the forces because of the pressure differential along the height of the body. So if the body was more arbitrary in shape, then what you'll have to do is, let's say the body was of some arbitrary shape, and you had to find the net force of buoyancy for this case. So what you can do is you can take vertical strips and then you can integrate. Okay, so the net force acting, so you can take a vertical strip and you can call its volume as d omega, and then you'll have to integrate over all these volumes uh, to find to find the total volume. And then what you can say is the net force differential across this, the pressure on these two surfaces. So to find the total force, you'll have to integrate over all such infinitesimal length elements. Okay, and you can use the same idea because the top surface of the solid may be curved here. So you can use the same idea as we used earlier of the force acting on a curved surface. The vertical force can be found out using the idea that we just discussed as the amount of weight of the liquid on top of it. So I will leave it to you to check for the force of buoyancy being equal to rho liquid times g times the volume of the displaced liquid for an arbitrary shaped body. Right. So just a food for thought for you. So let us say, you stand on a weighing scale and you measure your weight to be 60 kg. Okay, so you'll have to estimate the error due to the buoyancy of air. Okay, so air is also a fluid, so you'll have to estimate the percentage error in the reading that you find out. So remember that when you're standing in air, so the net force acting on you is mg minus that force of buoyancy because of air. So we assume that the FB is 0, but that is not the case. So in this case, you have to estimate a reasonable estimate based on any assumptions that you would want to take in terms of the volume that you have, and you find out what is the percentage error or the amount of kgs that is the error in the calculation or the measurement if you because you have neglected the force of buoyancy in this case. Okay, so please estimate that. This is just again food for thought. Okay, and some related ideas. Well, one major idea that that engineers are interested in is the idea of stability in buoyancy. So, for example, if you have a ship, let's say a ship which is floating in the sea, in the ocean. Now, the question for you is, would you want the ship to be top heavy or bottom heavy? So, does anyone want to answer this question based on intuition? So, would you want the center of gravity of the ship to be here or here? It's an open question. Okay, so let's analyze. So if you have, let us say, the ship as being top heavy. So let's say the center of gravity is here. Now, there's a net pressure acting on the floating part of the ship. And if you take the overall effect of that, then you can assume that it is concentrated. The net pressure force acting, or the net buoyancy force acting on the ship is concentrated at a point which we call B. And this B is called the center of buoyancy. Okay, so this is nothing but the center of gravity of the liquid that has been displaced by the ship, or center of mass, whatever you want to call it. Okay, so in this case, the force of buoyancy is acting upwards, and the force of gravity mg is acting downwards. So if you give a hypothetical rotation to the ship, let us say we give it a counterclockwise rotation, so the ship becomes like this. So what you'll see is the force of buoyancy will act here, and the force of center of gravity will act here, and you can see that this will topple the ship. So this position that you had here was not a stable position. Any slight rotation in any direction will result in the ship to topple. But for the other case where the ship is bottom heavy, you will see that the restoring torque the torque will be restoring. So it will restore it back to its initial position, so that position is stable. Okay, so this is a technique that engineers will use a lot to ensure that the ship does not capsize. Okay. But remember that there may be multiple stable positions possible. So this is it's not that the ship in only this direction is stable. It may happen that it capsizes and then turns upside down, and then that upside down position now becomes stable. And then it's difficult to, I mean, if anybody has done rafting or kayaking, you may have noticed that if a raft or a kayak particularly, if it turns upside down, it is difficult to turn it back, because now that upside down position is a stable position. Okay, so it's only for particular rotation angles that boat will remain stable. It will have a torque which will restore it back. But if you have a very large um, rotation, then it may not be able to turn it back, because you may reach some other stable position. Okay, I will quickly move ahead, because these, again, as I said, there's nothing new here that you're learning. These are similar ideas that you have earlier but applied to other problems. Okay. So now let us come to more interesting part of fluid mechanics. In fact, it's usually said that fluid statics is the trivial part. Okay. So today we'll start the first topic from this more interesting part, which is called fluid dynamics. And the first topic that we'll discuss, the chapter is called integral analysis. So I'll tell you what it means by the word integral analysis in fluid mechanics. So there are usually two different approaches to solving a fluid problem, a flow problem. Okay, and these approaches are decided based on the requirement that you have from the problem. So we'll say this is based on requirement. Okay, so what we mean is that let's take an example. So let us say that you have a Formula One car that you are designing, and you would want to find out that to maintain a particular speed in the car, what is the amount of fuel that you have to expend. Okay, so this is an integral problem, because what interests you is the total force acting on the car, the total drag force acting on the car because of the air. So I'll say finding overall force, etc. So it may be something else, overall that you are interested in. But what I mean in general is that you will deal with large volumes in this case. Or should I say deal with whole volume, full car. Now, it may also be possible that what interests you is to find the distribution of force on the car's surface. It may happen that certain parts of the car will experience more force than the others. And as an engineer, you would want to ensure that the complete surface, you have to design the strength of the surface in such a way so that it can take the forces acting. So rather than having a very strong material throughout, you will try to estimate in the worst case scenario what will be the force distribution, and then you ensure that the surface is only enough strong at that particular point. So you'll have a heterogeneous strength in the car's surface. Okay, so this analysis where you would want to find out the distribution of force as a function of the position is called differential analysis. I'll say find the fluid velocity slash pressure field. So we'll see that if we can find the velocity or velocity and pressure field in a fluid, then we can find everything else from that, which includes the force acting on a surface that is in its path. Okay. Of course, I mean the word integral and differential, they're coming from the idea of integration and differentiation. But this is the requirement-based approach taking. So in this discussion, in the first few lectures in this week to come, we'll be talking about integral analysis. And this is typically what is discussed first when you start analyzing fluid flows. Any questions? So before I start writing integral equations, let me first talk to you about certain ideas and concepts, because we'll require that understanding. So the first idea, again, we have briefly discussed it, but we'll have to expand on that, is the idea of a system versus a control volume. Okay, so we've discussed in the past that control volume is a fixed volume in space. Well, not really fixed, it can be moving and expanding as well, but it is a volume which is not fixed to the material. So if I had to take a certain, let's say, I take n number of molecules of a fluid. So let's say that we have an imaginary volume in space, and at a given time t, this volume had a total of n molecules of fluid. If I start tracking the behavior of these n molecules, then it's called a system analysis, because you are, like solids, you are stuck with a certain amount of molecules. For example, in solid, you talked about a block. So that block is nothing but a collection of molecules of solid that you're tracking in time. So you can do the same thing with fluids as well. So you can track a certain amount of molecules in time. But that is not what we typically do in fluids, because we're interested in spatial volumes, as we discussed earlier. So the word system will refer to a collection of molecules. And the good thing about system analysis is that your Newton's laws of motion can be readily applied to them. Because remember the laws of motion, for example, the second law, force equals mass time acceleration. is applicable to a system. So force acting on a mass is equal to the mass times the acceleration of this mass. Okay, so I'll mention Newton's laws of motion. So for example, force acting on the system is equal to the rate of change of the momentum of the system. So this is the kind of law that we are applying. The other law is that the mass of the system is constant. So you take these n molecules of fluid and you track them in time, you will see that that mass of those n molecules together will not change. Okay. The next is control volume. So if you have a car that is, let's say, moving on the road with a constant velocity v, so you can analyze this as a stationary car with the air moving against it with a velocity v. So the air is moving against it with a velocity v. Now to analyze the force on the car, you cannot track a certain molecule. So to find the force, well, force as a function of time, let's say, on this car, you will have to analyze all the air molecules that are hitting the surface of the car with time. So different molecules will hit the surface of the car at different times. So for this analysis, what you will do is you will form an imaginary control volume and analyze the behavior or the physics that is happening inside this control volume. Okay. Now, what we'll study or what we'll learn in the next lectures to come is how to relate a systems analysis to a control volume analysis. I just told you that you can easily write the force, the Newton's second law in the systems analysis. But what you really want is the control volume analysis. You would want to know the force acting as a function of time on the car, which is because of different molecules. So how can I relate the systems analysis to a control volume analysis? We'll discuss further as to what these words exactly mean. What is the meaning of analysis here? But on an idea level, this is what we'll be learning in this integral analysis chapter. Okay, so we will be learning the mathematics that is going to relate the two. We'll be learning equations that will relate a systems analysis to a control volume analysis. Just a reminder that this control volume that we're talking about is imaginary. Don't try to always relate it to something physical. In fact, it is completely up to your imagination. It is like this free body that you used to consider in previous mechanics analysis. So remember, if you had to choose a free body, rather than choosing a complete monkey that you had, you could even choose a half a monkey as a free body. But you'll have to consider the forces acting on that surface of the monkey that half monkey you consider because of the other half. So all the surface forces and the body forces have to be considered on that free body. Similarly, if you take a control volume, you'll have to consider all the surface effects around its region when you do the analysis. Okay, so just remember that this control volume is imaginary. All right, so these were the ideas we had to understand this discussion. Now, one particular terminology is what we'll have to recall. We already have learned that. Okay, and this is called mass flow rate. So if you have a pipe, then the mass flow rate, let's say through the pipe, is written in terms of kgs per second. So what's the amount of kilograms of liquid that is flowing in or flowing out of the pipe in a given second? That's the mass flow rate. Now, if you have, let's say, a surface, and the surface has an area A, and the velocity of the fluid through the surface, so there's some fluid flowing out of the surface, and the velocity of that fluid is given as v. Okay. And the fluid that is flowing out of a surface is not flowing normal, it is flowing at an angle, and that is completely possible. It can happen that the fluid is flowing at some angle out of the surface. Now, if I had to find the mass flow rate in this case, how will I find that? Okay, so what I can do is I can find the mass flow rate, which is kgs per second, by multiplying the density times the volume flow rate. So I'm assuming that the density is constant here. Okay, and the volume flow rate can easily be found. So it is only the normal component of the velocity, which we'll call Vn, that is resulting in a flow out of the surface. So we can write this as Vn times the area A. Okay, so the velocity is in meters per second, area is in meters square. So velocity times area gives us meter cube per second, and that multiplied by density, which is kg per meter cube, gives us kg per second. I can also write Vn as nothing but the dot product between V and the normal vector n hat. Okay, so this becomes my mass flow rate. Is that clear? So if I have a non-uniform flow, so earlier the flow was uniform. Everywhere in the area the velocity was V at the same angle. But let us say the flow is non-uniform. So what that means is the velocity V is at different angles or at different magnitudes for different areas on the surface. So for that, I'll have to integrate. So the mass flow rate is going to be an integral over the area A, and then I have to take rho times V dot n for this small area A, because this is your dA, and the total area is A. Okay, and in some cases we simply talk about the volume flow rate. We don't multiply it by the density, so that is simply V dot n times dA. And you can see that it is going to be positive if V dot n is positive. And we always define n hat in the outward as an outward normal. So what that will mean is if you're talking about the surface of a pipe, if the fluid is flowing out, then this is positive. And if the fluid is flowing in, the outward normal is like this, and the fluid is flowing in, so that becomes negative. So for inflow, it is negative. So remember that, otherwise it gets confusing. This is just a sign convention that you have taken. Is that clear? Right. So now we are in a position to tell you about the most useful and the most interesting theorem in fluid mechanics. It's called the Reynolds transport theorem, also written as RTT. So I'll need all your attention now, because it is, as I said, the most useful theorem in fluid mechanics. Okay, and this is what will help you to relate your system analysis to the control volume analysis. Okay, I will not tell you the theorem today, we are out of time, but what I'll tell you is I'll give you an example to first develop a feel for this theorem. Okay, so develop a feel for the theorem. So let us say you have a hypothetical control volume. Okay, and you have n molecules of air inside it at a given instant of time. So we'll call it at t equal to t1. So if I ask you what is the mass of the system of these n molecules, so I'm defining the system as these n molecules. So the mass of the system is nothing but the mass of the n molecules. Now if I ask you what is the rate of change of the mass of the system with time, does anyone want to answer this question? Remember, the system is defined using these n molecules. So at all times, the system still is these n molecules.
Sir, 0.
Exactly. The rate of change of the mass of the system is 0, because the system is always these n molecules. So the mass of the system will always be the same. So it is 0. Now I say mass of the control volume. So the mass of control volume is defined as the mass of air contained in the control volume. Now it may happen that at different times different molecules will move in and move out of the control volume. So if I ask you again what is the rate of change of the mass of control volume with time? Now this may not be 0, right? Because assume that your control volume was a box, a metallic box, and you were pushing in air, or you were pressurizing air into the box. As you put more and more air, the number of molecules inside the box are increasing. So the mass of the control volume is increasing with time. So dmCv by dt is positive. Okay. So this may not be 0. Now, we talked about mass, but it could be any property. Okay. Well, we just took an example for mass. So the question is, how do we relate d by dt of the system property and d by dt of the control volume property? Now, in this case, it's mass. So we already know that the d by dt of the mass of the system is 0. So we can easily find that the d by dt of mass of the control volume is simply the net inflow through boundaries. Okay, so this was an example we took to develop some feel for the theorem. We haven't told you what the theorem is. Okay, so this was all intuitive that we just talked about, but the language we used is going to be the same language as we'll be using for the control volume for the Reynolds transport theorem development. Okay, now as I said that this property mass that we took was a particular case, so we'll be interested in more general property. So we'll denote the general property as B. Okay, so B is an extensive property. So I'm sure you understand what the meaning of extensive is. Extensive properties are properties which depend on the amount of the fluid. So an example would be mass. So mass is an extensive property. More fluid you take, more the mass. Or momentum. The more fluid you have, the more its momentum. Okay, and the corresponding intensive property which is defined as beta is d capital B by dm. Okay, so this would be 1 if you're talking about mass. Rate of dm by dm is 1, and dp by dm, so the corresponding intensive property for momentum is velocity, and so on. Okay, so this is not the end. So what we'll be interested in this discussion on the Reynolds transport theorem is to relate dB by dt with dB control volume by dt. So in many cases, it is of interest to measure the amount of B contained in this imaginary control volume that we're talking about. But our physical laws allow us to find out the d by dt of B of the system that is contained in that control volume at some given time. So how do we relate these two mathematically so that we can solve plenty of fluid mechanics problems is what we'll discuss in the next lecture in Reynolds transport theorem. So we'll stop here today, and in case if you have any questions, feel free to ask.
Sir, can you explain that question about there being an error in the reading of the weighing machine again?
Right. Okay, so somebody is standing on a weighing scale, and you measure, the weighing scale says you are 60 kgs. Okay, so what the weighing scale is measuring is a net downward force, or the net force you're applying on the weighing scale. So if you draw the free body diagram of the person, then there is an mg acting, and what we're assuming is that this mg is equal to 60 kg, but that is not the case. You have an mg and you also have a force of buoyancy because of the air around you. So it is actually mg minus force of buoyancy that is given as 60 kg times so what I asked you was to estimate the actual mass, which in this case is not 60 kg. It's going to be more than 60 kg.
Well, sir, if we are standing on the surface of the weighing scale, then there isn't much air there between the surface of our feet and the weighing
You
scale.
think about it. I mean, spend some more time with it. Imagine that you were standing in liquid. So it was a pool of liquid. You had a weighing scale at the bottom, and you were standing on that weighing scale. So you can take a more uh, stronger situation and try to estimate the mass, given that the weighing scale shows 60 kg in water.
Okay, sir.
Okay. Right. So I'll stop the recording now.